Hey folks, so usually I post videos of the finished product after I've been working on these old radios, but I thought it'd be interesting to post the process. So record a video of the process and post it as we go. So this is an old RCA Victor that a friend of mine has given me to work on, and first thing we notice is that the power cord is completely shot. So we'll have to replace that. That's very common. These dry out. Okay, so let's take a look at it. Wooden cabinet, because they're hot chassis, and it's a Nipper II, Canadian made, CSA approval, good to know. One thing I always look for is if there are any missing screws, it tells you whether it's been worked on. No missing screws here. They probably have taken this off to replace the tubes at some point in its history. But that could suggest, oh, that might have been worked on. We'll see. Anyhow, let's take a look at the bottom. Okay, so there we see Nipper II, location of radiotrons, and so 35W4 rectifier, 50C5 power tube, and it's using the 12 volt smaller tubes. 12AV6, 12BE6, 12BA6. So this is a very common setup. This is the All-American 5 circuit, as they call it. And this would be later because it's using the 12 volt filament tubes. So this probably would be about early 1950s. Anyhow, we'll check out the model later on and we'll find out. And here's a little notice. When you replace your tubes, make sure you replace them with RCA, otherwise the radio won't work. Oh, you can see here, we've got some felt on there, not sure. And then, anyhow, we'll take it apart and see what's going on inside. Well, as I look closer, these screws are a little bit stripped, chassis screws, so clearly it has been taken apart at some time, which is extremely common for a radio 60 years old that's still working. Obviously somebody worked on it at some time. Anyhow, let's see. Okay, so here's the chassis out, your standard 5-tube chassis, and oh, shameful. Someone replaced the tubes with non-RCA tubes. So we'll take a look here. Looks to be in very good shape indeed. The speaker's in great shape. Very unusual, that's often in bad shape, dried out, but this one's great, and things look good. So we'll give the tubes a test, and maybe we'll flip it over and take a look at the other side. Okay, so it's not quite as pretty on this side. You can see, first of all, these original wax and paper capacitors are in pretty bad shape. They're all going to come out. They'll all be replaced. That's very common. Wow. What's going on there? So this is still this oscillator coil's just hanging here. That's unusual. Don't usually see that. This electrolytic capacitor has clearly been replaced at some point. That would not be original. Wouldn't look like that. And you can see up here, it is bulging. So that's got to go for sure. I hope I have some. What is that? 50 and 30 microfarads. We'll take a look at the original schematic and see what it originally called for. I'm guessing it wasn't 50 and 30, but we shall see. So that would have been replaced. See if I can find a date code on that somewhere. Oh, 50. Yeah, where's the date code? I'll take a look later and we'll find out. Here's another thing that you see quite often on these old radios. Some repair guy has written the tube type next to the socket. So there's a 35W4, that's your rectifier. Anyhow, that would be your power tube there. Oops, sorry, bad camera work. Well, it turns out I was wrong. That was indeed the original capacitor, and now that I look at it, it's a TCC, which is the same brand as these capacitors here. And the date code on it is September 1951, which is about right for this radio, so this would be the original capacitor. Definitely has to be replaced. The output transformer is in pretty rough shape, but hopefully it works. We'll do probably some testing at some point. And anyhow, there's work to be done on this radio for sure. Okay, so I have my ICO 667 tube tester, and we're going to test the tubes. I won't bore you by testing all of them, but we'll start with the power tube, which I have in right now. We have it set up, it's heating up. I have all the settings set to go. Interestingly enough, the 667 was preceded by the 666, which is known as the Devil's Tube Tester. So anyhow, the way that this tube tester works is you set all of your pins here for the grid, plate, and so on. You set your grid voltage, test grid voltage, your plate voltage, line adjust, filament voltage, 50 in this case, and we'll test on here. And the first thing we're going to test for is for leaks. So let's see whether any of the elements are leaking current. So we'll start with pin 1. Okay, and that's normal. So I'm going to press this button and we'll see if there's a leak. Okay, so we do actually have a leak in this case. It's at 1 megohm, which is a little unusual, but it's actually okay in this case. For this use, 50K is normally the threshold for rejection. So there is a leak between, in this case, between the heater, the filament in other words, and the cathode, but we might be able to get away with it. But that means this tube has been well used. So let's see what happens. We're going to continue test some of the other. So that's fine, and that's, ooh, it's a little bit. Should be okay though. There's that, yeah, and 7's okay. So a little bit of leakage there. We're going to check now using this merit button. We'll see what the strength of it is. So 80. So that's not too bad. I think we can get away with that. Okay, so we're through with the testing, and here's what we've discovered. The power tube is 70, it scores at 78. 100 would be a good new tube. So that's probably usable. It's definitely on the low side, but we can probably get away with that. The rectifier is fine, scoring 114. The 12AV6 is the detect. It has two halves of it. One half is the detector, so it sort of, how to explain that? It converts the signal, if you like, into an audio signal, and the other half is the first amplification of that audio signal. That's very strong. That's very strong. So the 12AV6 is great. The 12BE6 is what's called the converter tube. So that takes the signal in from the antenna, mixes it with the oscillator signal, does some fancy stuff, and spits out an IF signal. That's very low. So we're going to have to replace that tube. One half is 18, the other half is 28, so extremely low. The 12BA6, which amplifies the intermediate frequency signal, is 68, which is low. We can probably get away with it for now, but if we have a very poor reception, we might have to replace that. So for now, the only tube we definitely have to replace is that 12BE6. Pretty sure I have an extra one around somewhere, so we should be okay. Okay, so the first thing that we're going to do is replace this power cord, and as you can see, it is in very bad shape. What happens is the insulating material becomes brittle and dry, and it cracks, and then you get the wires showing through here. So the power cable comes in here. One end goes to the rectifier, one end goes to the switch on your power switch. So we're going to be replacing that, and what I use for that is I simply use dollar store extension cords. Cut off the end and away you go. You're good to go. You have a polarized cord and away we go. So through the magic of video, I will do that replacement now. Okay, so the power cord has been replaced, and in the process I discovered that the heater wire between the rectifier and the power tube here was very brittle and was falling apart, so I replaced that as well. So I think next we'll be looking at replacing the capacitors. So there are three types of capacitors in this radio. We've already talked about the electrolytic capacitor here. This is the power supply filter capacitor. It actually exists of two caps, a 50 microfarad and a 30 microfarad cap. Now, I don't have any of these double caps. They don't make them that often. They're quite expensive to buy. So I'll be replacing them with individual caps. Normally I would use a 47 microfarad here, which is the modern equivalent. Unfortunately, I'm all out of those, so I'm going to be using these two 22 microfarad in parallel to give me 44, and then I'll use another 22 to replace the 30. So not exactly the same, but in this particular instance, it's not that essential to have the exact values as long as you're within that certain range. Well, also, the other second kind of capacitor that we see in here are those paper wax capacitors, and I'll be replacing those with these, which are modern polypropylene capacitors, much smaller of course than the originals. The third type of capacitor that you'll find in here are these little ones that look like dog bones. And they're a form of ceramic capacitor. Quite often you'll see mica capacitors in here, which are very, very stable, and typically I wouldn't worry about them. The ceramic ones, I'm not quite sure. I don't think they're as stable as the mica ones, but they're very small values, and I'm not going to mess around with them. So again, with the magic of video, let's make those changes. Well, as you can see, the bad capacitors are out and the good capacitors are in, and I think we're about ready to do the first audio test before we do an alignment. First, let's find out if this thing actually works. Well, hey, I spoke too soon. Remember I was talking about how wonderful the condition of that speaker was. Look at here. It has cracked. So we'll have to fix that. A little bit of glue actually is the typical way to do that. It is actually, in fact, very fragile. I thought it wasn't, but it was. That's life. Well, I guess I better learn to keep my mouth shut when I'm talking about the condition of these things. This actually is very, very fragile, and in fact we might end up having to replace it. It's very dry. I thought it was okay, but it wasn't. It just looked good. Anyhow, we'll see whether that works. In the meantime, let me show you the safety devices that we're going to be using as I test this. And we begin with an isolation transformer. So as the name suggests, this isolates your unit under test from your earth ground or from your ground in your house. So you're less likely to get a shock, if you like. You can still certainly get a shock by grounding within the device, but not if I'm grounded to something in the house and touch it. And then connected to that will be a variac. So we will gradually bring up, using this variac device, we'll gradually bring up the voltage, so we won't be starting on 115 volts. So we can see how it performs as the voltage increases. And then connected to that will be this, which as you can see is not a light, but a current limiter. So this is what's called a light bulb limiter. It's kind of a homemade device, and it puts this light bulb in series with this socket. So why is that important? If I've screwed something up and there's a short circuit in the radio that suddenly starts drawing a lot of current, it'll be in series with this light bulb. So this light bulb will, if you like, suck up or use some of that current so that all of the current won't rush into the radio and blow something and kill someone. So anyhow, these three devices then will be connected together, and we'll hook up the radio to that and see how it goes. So I've replaced that 12BE6 tube with a slightly better one. Not 100% for sure, but certainly better. And the isolation transformer is turned on. The variac is on. We see the line voltage is around 118 or 115 or so. And our light bulb limiter is in series. We're ready to go. And I'll gradually bring up the voltage on the variac. We'll keep an eye on the light bulb limiter. Make sure we're turned up here in the radio, and we'll watch, see whether those tubes here begin to light up. Okay, we're up to 90 volts now. You should be seeing some activity here. And there we go, as the tubes start conducting. At least we have some noise for sure. No smoke. Okay, we're up to full voltage. Let's see whether we can pick up something. There you go. All right. Not too bad. So I guess we're good to go, and we will do an alignment next. Okay, we're all set up to do an alignment procedure, and this is the procedure for this particular radio, which is pretty common. So in an alignment, you send a test signal of 455 kilohertz to your radio, and you're adjusting these, which are called intermediate frequency cans, IF cans, so that they resonate at that frequency, and that will help the radio in terms of receiving and translating, if you like, that signal into an audio signal. And in order to do that, we're going to use this device here. Oh, let me get some light on it. This is our signal generator. It's set up right now for 455 kilohertz on band B. It's going to put out a modulated signal through here, and I have this multimeter attached to the output so that we can measure the actual output. Okay, I'm not going to keep this on too long because I know that that's a very annoying sound, but that's the sound of the modulated signal, and we can adjust this. Normally you shouldn't use a metal screwdriver to do this, but unfortunately with this one, my ceramic screwdriver doesn't really work. So I'm looking to see that, to peak that as much as possible. So we're up to so you see we are increasing the ability of this radio to receive, if you like, and to convert the signal. Okay, so I think I've peaked there at 101. Okay, and I'll do the other side and so on.
Deb in the morning.
They get me
Well,
going
the radio's all
every
back together, aligned and back together, and
Real 103.5 KHJ.
doesn't sound too bad. There we are. All done from start to finish.